I'll talk about a completely different topic, which is the tensor renormalization group study of gauge theories. For the purpose of this talk, they will be completely disjoint. I won't connect them, but they can be obviously, there are some intricate relation between them. So I'll just start with a brief overview of what I'm going to talk about in this talk. Firstly, I'll talk about the basic ADS-CFT correspondence, and then I'll talk about the generalization of ADS-CFT correspondence to the cases where the number of spatial dimension is less than 3. So P is for the number of spatial dimension, and I'll talk about the lower dimensional gauge gravity dualities, and those correspond to the non-conformal cases. As we know, for P equal to 3, we have the famous N equal to 4 superangles, which is dual to ADS 5 cross 5 sphere. So there are equivalent descriptions in lower dimensions, even though there are non-conformal theories, so I'll talk about those. Moving on, I'll talk about the lattice formulation of N equal to 4 superangles theory, which has been a work in progress for the last decade or so. And the motivation for that work is to understand the strong coupling features of N equal to 4 superangles in 4 dimensions and connect to the holographic dualities. Moving on, I'll show some results for matrix models, particularly BFSS and BMN matrix model. And I'll talk about the 2-dimensional 16 supercharge theory, which is also the maximal supersymmetric angles in 2 dimensions. And then I'll move to the second part of the talk, which will be about the TRG applications to 2D non-abelian gauge Higgs model. And to finish off the talk, I'll talk about some future directions and the work which I want to pursue in the future. Okay, so the basic gauge gravity duality, we are most familiar with the ADS-CFT correspondence, which connects this 4-dimensional N equal to 4 superangles theory, which is associated to a world volume of D3 branes in type 2b supergravity. And it is dual to this supergravity theory on NT-de Sitter 5 cross 5 sphere in the decoupling limit. So by decoupling limit, I basically mean that the rank of the gauge group, or the N, SUN gauge group N, is large and the coupling is strong. And that is the basic ADS-CFT correspondence. Just few months after the initial ADS-CFT correspondence, it was extended to a lower dimensional maximally supersymmetric angles theory in, say, P plus 1 dimensions. And those are considered to be dual to DP branes at low temperatures. That means there is a dual description in terms of type 2A or 2B superstring theory, low energy string theory, depending on whether we have odd P or even P. In this talk, I'll not talk about the cases where P is greater than 3, and I'll completely restrict myself to P less than 3. So let me just start with the N equal to 4 superangles action. We have F mu nu square, and then you have the kinetic term for the scalars, and then you have commutator term, and then you have the fermionic part of the action. This theory is a SUN gauge theory with 4 fermions, and it has 6 scalars, and those are coming from the dimensional reduction from N equal to 1 in 10 dimensions down to 4 dimensions. And they are all massless and in the adjoint representation of the gauge group. This theory is supersymmetric and has 16 real supercharges. The fields and the supercharges transform in the global SO6 R symmetry group. The special thing about this theory is this theory has a line of fixed points, so it is conformal for all 't-Hooft coupling, where 't-Hooft coupling is defined as the G angles square times the N. And for this theory to be dual to the classical supergravity in ADS-CFT correspondence sense, we need planar limit and strong coupling. So we need N to be large and lambda to be sufficiently strong. So let me just briefly show this phase space of, say, for example, superangles theory in N lambda plane. So corresponding to the vertical axis, which is the N, and N corresponds to the G string corrections on the supergravity side. So if I take N to infinity, Gs is going to 0. And on the horizontal direction, I have the 't-Hooft coupling, which is related to the alpha prime correction. So large lambda means you are suppressing the alpha prime correction. And for small values of lambda and, for example, N equal to 3 and the planar limit, we have the perturbation theory. When we go to large values of lambda, and if the fermions are in the fundamental representation, like for example, say in QCD, you have this quark-gluon plasma around lambda of 10 and the SU3 gauge group. But when you go to the supersymmetric version of this theory, and you take large n, you have the planar 't Hooft limit, which is the low energy string theory, where you have alpha prime and GS going to 0, and now the fields are all in the adjoint representations. Fermions are in the adjoint representation. So what is the motivation of studying these theories numerically on the lattice, for example, n equal to 4 superangles, is to explore the region in between. Because on the lattice, we can do finite n and finite lambda, and that is going to be an input to the results from the superstring side, because we'll get to know more about the 1 over n or 1 over alpha correction. So this entire region is the interesting place to do lattice calculations if one can do it reasonably well enough. So this is the basic idea. So lattice n equal to 4 superangles has been, people have been working on this for the past 2 decades or so. The initial motivation was to use something which works for QCD and apply it to supersymmetric theories. So the obvious choice to do strong coupling n equal to 4 was to use lattice and apply it to SUSY theories. But unlike QCD, supersymmetry on the lattice is very complicated. And the complication comes from the fact that there's a supersymmetric algebra, which is the extension of the Poincare algebra, which we know. And that is classically broken on the lattice because of the algebra between the supercharges. The field content is huge for all these supersymmetric angles theory. There's a conformal symmetry. And the holographic limits, which we talked about, are lambda going to infinity and n large. And those are the region which is exactly very difficult to do numerical simulations of. And in addition to all those, there are fermions which are often a problem to put on the lattice and simulate. But in the last decade or so, there have been some very wonderful ideas coming from different directions, which have at least helped us reformulate this theory on the lattice by preserving some subset of the supersymmetries. These ideas are the ideas of twisting of a supersymmetric theory, which I'll talk about later. And then the idea of the Kähler-Dirac fermions. The Kähler-Dirac fermions are like fermions which are like P forms, integer forms, not half integer, but P forms. So they are useful in this construction. And then we have a very interesting lattice, which is called A4 star lattice, on which we describe this 4-dimensional theory. It turns out that the requirement for A4 star lattice is to ensure that when you take the continuum limit, you don't have to fine-tune a lot of terms. So this A4 star lattice has a point group symmetry which prohibits the terms which you have to fine-tune in order to get the right continuum limit. For a nice review, you can see the reference mentioned above, which is by, so a lot of people have worked on this, most primarily David Kaplan and Simon Catterall. So I talked about the topological twisting and how is it related to the study of n equal to 4 superangles on the lattice. So the idea of the topological twisting goes back to the work by Waffa, Witten, Yamron, and Marcus back in 90s. And the basic idea of this twisting procedure is that you have an R symmetry group in n equal to 4, which is SO6. So you identify some subset of that R symmetry group, say for example, which is SO4 in this case. And then you have the SO4 Euclidean rotation group. So you take a diagonal of that Euclidean rotation group and the SO4 subset of that SO6 R symmetry group. And you define a new group, which is written here as SO4 twisted. So this is a maximal twisting of the n equal to 4 superangles, which was first written down by Marcus in 1995. So what this does is, you start with some SO6, but now you say that all the fields are going to transform in this SO4 twisted. So what this does is, now all the fermions which we had in the original theory are now mapped to integer spin with this under this new rotation group. So doing this twisting procedure is nice because it gives us a scalar supercharge, which is the zero form fermion. For example, the 16 supercharges of the original theory can be broken up into 0 form, 1 form, and 2 form. We have 1 0 form, we have 5 1 forms, and we have 10 2 forms. They add up to 16. And this is the one supercharge which is exactly preserved on the lattice. This construction is exactly similar to the one which we get by Orbi folding of the supersymmetric theory, which was due to Kaplan. So this scalar supercharge, which we are getting by this construction, is the supercharge which we try to preserve on the lattice. So we start with a theory, n equal to 4 superangles theory with 16 supercharges. But we know that we cannot keep all the supersymmetry intact on the lattice at a finite lattice spacing. So we make this twisting procedure and keep this scalar supercharge, which is exactly preserved on the lattice. In fact, as we'll see in the next slide, not all supersymmetric theories can be studied in this way on the lattice. There are several hard restrictions on the theories which we can study. And in fact, n equal to 4 superangles is the only theory in 4D which you can study by this construction on the lattice. But there's no complaint here because this is probably the most interesting 4-dimensional supersymmetric theory which we know of. Yeah.
Are you in this procedure defining a new theory and saying, let's study this new theory? Or are you saying, this is just an interesting way to organize the field?
Yeah, so
by using that, I'm going to be able to put it on the lattice and preserve a supersymmetry.
Yes, so this is an interesting way of organizing the theory, but it turns out that in the flat space, the theory you get before twisting and the theory you get after twisting has identical properties, but on a curved background, it is different. Oh. So in this sense, if I'm on a flat space-time, I'm rewriting a theory, but the theory is not getting different. It's the same n equal to 4 superangles theory which we have.
In the lattice formulation, is there any distinction between buffer-within twist and geometry relevant twist?
Yes. So the twisting I am mentioning here is the one by Marcus. Now, you can twist a supersymmetric theory in a different way. How you twist a supersymmetric theory depends on what subset of the R symmetry group do you want to identify. Or in this case, I am identify SO4 subgroup. So SO4 is the maximal we can go, right? Because then only we can take a diagonal with the SO4 Euclidean. So this is the maximal twist, which is because of Marcus. When you go to Waffer-Witten twist, that twist is non-maximal in the sense that in that the group which is recognized is smaller than SO4 subgroup. So it turns out that we need to do the maximal twist to put it on the lattice. We cannot construct n equal to 4 using any other twist. It's only one of the 3 twists that work in this case, which is the one by Marcus.
Don't the theories have different spectra?
Sorry?
Don't the theories have different spectra?
On the flat space-time, there are arguments that they're the same. That is what I know. If I'm sure that they're on curved background, they're different, but on the flat space-time...
I guess I was thinking, maybe the vacua are the same, but the excited states...
Yeah, the excited, yeah. So at least we are, excited states, the vacua are the same. And I think that is what we, like, as a first pass, we are trying to just understand, like, we are not thinking much about the excited state in this sense.
But the spectrum of operators, probably, maybe this is related to your question, the spectrum of operators from the field theory perspective is probably different, right?
Even in the flat space?
No, I'm just asking, if that's the case, then once I study anything like finite temperature or something, I would expect there is a difference between 2 theories.
Yes. But, so
that's why the question of the spectrum is an important one. It means there is no really decoupling of the excited state.
And because you're at finite lattice space, and the gap is finite, it's not.
Yes.
It's not infinite.
No, in the sense that as I take the continuum limit, I think, at least that's my understanding, that this twisted subgroup will reproduce the same properties of the n equal to 4. For example, if you calculate the Witten index, you get the n and other things for this theory as well as for the untwisted.
Yes, but that's vacuum.
Yeah. That's topological.
Yeah, but for excited state, I'm not sure about the excited state,
But is it that there's an overlap, so that if I calculate some particular correlator in your theory, that would be the same as the correlator in the theory?
So till now, what we have done is that we have matched with the perturbation theory results from the n equal to 4, and with this construction, we get results which are completely consistent with the perturbation. For example, we calculated the static potential, for example, in perturbation theory.
Between external quarks?
Yes, exactly. So we can calculate that by using the correlator, and those things agree in the perturbation theory. So there's some hint that it's not, there's some in the limit which we are working, we reproduce the perturbation theory results. So we are a little confident that this is not outrageous in the sense that twisting is not taking us too far from the original theory. I won't be showing results, but we have obtained results for the static power potential, even for the anomalous dimension of some of the Konishi operator and so on. You see that they are consistent with perturbation theory. Okay, so I mentioned in my previous slide that not all theories can be studied on the lattice. And the reason is that the theories which can be studied on the lattice need to have at least 2 to the power d number of supercharges. So for example, in 2 dimensions, I can study 4 supercharge, 8 supercharge, and 16 supercharge theory. And in 3 dimension, I can just study the 8 supercharge and the 16 supercharge theory, while in 4 dimension, I can just study one of the theories. And that is related to the idea that the R symmetry group should be sufficiently large to do this process of maximal twisting. And when we break the fermions into 0 form, 1 form, and 2 form, that the breaking should, the initial theory should have sufficient number of supercharges. Otherwise, I cannot make that decomposition. So these are the only theories which we can study on the lattice, and we have been studying most of the Q equal to 16 supercharges in 2 and 3 dimensions because they take part in the holographic dualities. So since I just mentioned about the ongoing work in 4 dimension, I won't be talking about 4 dimension because we don't have any results away from the perturbation theory yet. But in lower dimensions, we can do much better, as I'll show you in this talk. And when we start from this 4-dimensional n equal to 4 superangle theory, there's option of going all the way down to 0 plus 1 dimensions with 16 supercharges. And that gives us the BFSS model. And that model has 16 supercharges. There's another variant of this matrix model, which is by adding a mass deformation to the BFSS model. And that is a matrix model on a different background, which is known as the PP wave background, which is known as plane wave matrix model, PWMM, or BMN model, after the name of the authors that proposed this model in 2002. So these are the 0 plus 1 dimensional quantum mechanical supersymmetric models with 16 supersymmetries on different backgrounds. So BFS is on a flat and BMN is on a PP wave background. The another possibility is to reduce the 4-dimensional theory down to 2 dimensions and study the super-Yang-Mills theory, which is dual to type 2 supergravity, and study the different black hole solutions, which is available in that theory, which I'll talk about in more detail later on, which are known as uniform black string and localized black hole solutions. And there is some sort of a transition between them. So holographically, on the gravity side, you think that you have a transition between the black string solution and the localized black hole. And on the gauge theory side, we should reproduce that same transition in terms of the confinement-deconfinement transition. So I'll show some results that we see the exact holographic dual of that transition in the gauge theory using lattice simulation in 1 plus 1 dimensional super Yang-Mills. Now, it is interesting before doing numerical simulations to understand what exactly is the regime of validity of the supergravity in p less than 3. For example, when p is equal to 3, it's a conformal case. And in conformal case, you have a valid description for all the lambdas. For example, any value of Thooft coupling at sufficiently large, you can have a description. But when you go to lower dimension, the constraints so to have a valid supergravity description, we need to satisfy 2 of the conditions. One of the conditions is related to the alpha prime correction, which I mentioned in the phase space diagram. And the second is related to the G string coupling. G string should be much less than 1. Alpha prime just means that the lambda should be much greater than 1, and the G string less than 1 just means that the n should be large. So these 2 combined in lower dimension gives me this inequality, which I have to satisfy for the coupling if I want to probe the type 2 supergravity. That is, the coupling normalized by the dimensions according to what dimension we are looking at, lambda p beta 3 by p, where beta is inverse of temperature, should be less than this specific power of n. And as we can see, if we just put p equal to 3 in this case, we just get the usual limit in 4 dimension, which is that the n should be going to infinity faster than lambda. And this is what we'll use in lower dimension, and we'll always make sure that we are in this regime when we are looking at the supergravity predictions from the gravity side. So let me now go to the 0 plus.
What was beta?
Beta is inverse temperature. So it's like a scale you use to make the coupling, introduce a dimensionless coupling, because lambda p in p less than 3 is dimension full. So you use a beta, which is the time direction and inverse temperature to make that dimension less.
The gravitational solutions are.
Yeah, that beta is equivalent. It's like the inverse of the Hawking temperature, if you want to think of that in terms of the supergravity solution. That is the inverse temperature. So let me just now move to this BFSS matrix model. So BFSS matrix model has the action is written like this, where you have two bosonic components and two fermionic components. So kinetic term for the scalars, and then the commutator term, and then you have a fermionic kinetic term and the Yukawa term. And this model can be obtained by the dimensional reduction of n equal to 1 supersymmetry in 10 dimensions down to 0 plus 1 dimensions. And now in this action, I and j runs from 0 to, in fact, it should be from 1 to 9, runs from 1 to 9. There are 9 scalars. And we have a total of 16 psi fermion components. And all the fields are in the, all the fields are represented by n matrices and are in the adjoint representation of the gauge group. So we have 9 scalars, we have this SUN gauge symmetry, and we have bosonic and the fermionic piece, and they're related by 16 supersymmetries on this flat spacetime. So I have not done any work on this, but I'll show the state-of-the-art lattice results which were obtained by groups in Japan and US. So this figure is from this archive number, and this plot is very interesting in the sense that the black curve you see is the supergravity prediction. So black curve here is the result which you get from the supergravity calculations on the gravity side. And the coefficient of that leading term is known from the supergravity. It's some 7.41. But we already mentioned that finite T corrections are corresponds to alpha prime corrections in this type 2 string theory. And then once I go to moderate couplings, I see that the lattice results are starting to deviate from the supergravity prediction. So it's not hitting the black curve, which is the leading supergravity prediction, but it is following some other trajectory. And what we can do is we can ask the question that what is it this corresponding to in terms of alpha prime correction? Now, there is no input to this from the supergravity side, because from the supergravity side, because of the work by Gross and Witten, it's only known that the leading correction, if finite alpha prime corrections start at the order alpha prime to the cube. So this is known from the work on supergravity side, but the coefficients are unknown. So what these authors tried to do was they tried to fit the coefficients of this alpha prime to the cube to the results which they got. And they did this to alpha prime cube to leading order alpha prime to the cube corrections, and they found the value for this constants which is mentioned here as A1, A2, and so on. So this constants A1 and A2 is completely unknown from the supergravity side, and this was, they mentioned that this is like a input from the numerical point of view to the supergravity result, because this has not been this is a non-trivial evidence that we can produce this coefficient of the alpha prime correction from the lattice result. And for this calculation, this is just a time direction, right? 0 plus 1 dimensional BFSS model. And they use n equal to 32 and L equal to 32. So 32 sites lattice, and they used a SU32 gauge group. So unless you go to this such large values of n, we have seen that you see a lot of instabilities in the numerical results, and you just cannot reproduce or even get closer to the supergravity prediction. So you need to have the n which is sufficiently large, in this case 32.
So
Yes?
Can you comment? So has this collaboration been able to show that alpha prime square coefficient is 0? The earlier one, just from numerics.
I don't know whether they have that in the paper, but they told me they tried to fit it to the alpha prime and alpha prime square, and they saw that it was vanishing. They had huge errors on those things, but it was consistent with 0. So they just set it to 0 and just fit it to the alpha prime cube. That is what those collaboration people told me. So, and once they fit to this alpha prime cube, they got some number which I don't quote here, but that is somewhere in this ballpark of like order 5 or something like number.
But I guess the question is, can we trust that number at all, given that they don't have, according to what you were saying, it doesn't look like they have control over. Normally, you would have to fit it with a cubic polynomial, I would say.
Yes. So
you have to have very good controls.
So they have all the data in their paper. So looking at the data, I think I don't know. I don't know whether I can trust them, but it seems like when they showed results from, for example, say n equal to 16 or 18, it was not even like you couldn't do any sort of fit. So it was. They have this argument that as they go to large n, they can do this. So it's just argument they're making that at n equal to 32, we could do that. But we cannot do n equal to 32, so I don't know whether there's a way of checking their results explicitly. But in any case, this is even if this is not completely correct, this is just a nice motivation that you can produce something which is not known from supergravity side just by doing a calculation of the strongly coupled gauge theory. So strongly coupled gauge theory can tell you something if you do it, for example, in 0+1 dimension about the corrections which you can have in the alpha prime or n from supergravity side.
Just before you go, you're measuring T
it's dimensionless. It's
in units of string scale.
So this T is the normal usual T divided by the Thuft coupling 1/3. So this has been made dimensionless.
Okay.
This has been made dimensionless by rescaling by appropriate factors of lambda.
Lambda.
Yeah.
Okay.
Yeah. Yeah. Sorry, I should have mentioned. Thank you. Okay. So now the interesting thing is that in BFSS you don't have any phase transitions. For example, in BFSS you just have a deconfined phase, and that is true for all values of lambda, in which you can be in the supergravity regime. But on the other side, BMN is an interesting candidate in the sense that it has a phase transition. Now, understanding theories, holographic theories with phase transition is more interesting because it can tell you about different black hole solutions on the gravity side. So for example, in BMN, there's this prediction that this plot is from this paper by Costa, Penedones, Greenspan, and Santos. They did a gravity calculation and they mapped out the phase structure of the BMN model, and they found something like this. They found that at G to 0 limit, the phase transition is happening at T by mu of 0.076. I'll mention what T and mu are in the next slide. And they saw that as they move to stronger coupling, this critical temperature moved to this value of 0.106. So they found this value from gravity calculation, which is shown here in the bold line. Now, we know the free field result and we know the gravity prediction at very large values of G. But what we really need is to understand what is happening in between. So this problem is in some sense like the problem which we already know in 4 dimension, where the free energy has a factor of 3/4 between free theory and a strong coupling limit. And the interpolation form of that function between 1 to 3/4 is not known. It's something similar which is happening in this BMN model, where the intermediate structure or the interpolation form is not known. So we thought of studying this, and I'll show you some preliminary results for this model. And this model is just a deformation of BFSS. So let me just mention the action in this case. So we start from the BFSS action. And in BFSS, you have a SO9 symmetry for the scalars. So there are flat directions. But in BMN, those flat directions are lifted by adding these mass terms to the scalars. So you add mass term to the SO3 part, and you add a different mass term to the SO6, and you have a splitting of the SO9 symmetry down to SO6 cross SO3. And then you have a cubic term in X, which is known as Myers term, And there's a fermion term as well, which is given by that expression. And all of these depend on mu in some way. For example, so you can think of BFSS as mu to 0 limit of BMN. So in this model, again, the basic idea is that this model is dual to M theory on a different background, which is PP wave background. And even after the addition of this mass deformation terms, the supersymmetry is intact. That is the most important thing about this model, BMN model, is that even after adding this mass terms, the supersymmetry is still intact because you modify the supersymmetric transformation by going to a different space-time. Again, the dual classical supergravity regime is valid when n is large and coupling is strong. So now we use a naive discretization to study this theory on the lattice. This is a work in progress. And the idea is to understand this thermal or the deconfinement transition for which the order parameter is the standard Polyakov loop. This is a finite volume phase transition, but we can have a finite volume phase transition because we are working in the large n limit. In fact, I've just recently begun to appreciate the fact that in some cases, this thermal deconfinement can also be, in some cases, entanglement entropy can also be used as a order parameter for these transitions. So Ru and Takanagi have argued that in some cases, the entanglement entropy plays the role of an order parameter similar to the Polyakov loop, which is mentioned here. So there are two phases, P not equal to 0 is the deconfined phase, P equal to 0 is the confined phase. We'll first explore the free G to 0 limit, which is the perturbative results, and we'll see whether we agree to that, and then we'll move to higher couplings. So these are the preliminary results. So I should mention what these histograms here are meant to be. So there are two phases of the black hole in this case. So there's one which is localized and one which is uniform. So as you can see, these are the eigenvalues of the Polyakov loop. For example, the eigenvalue of the Polyakov loops is related to how the black hole solution looks like. For example, if you have a uniform distribution, that just corresponds to a uniform black string on the gravity side. And if you have a localized distribution, that means that you have a localized black hole. For example, in this case, you see that as you go to SU12 and SU16, you're more or less becoming, you have a uniform distribution. But as soon as I go to a different regime of the parameter space, it becomes localized. So this is just a measure of identifying which solution or which region of the parameter space I am in. For example, if we get something like this, then we can say that it is closer to the uniform solution in the gravity phase. And if we get something like this, we can say that this is in the localized phase. So this is a nice, the eigenvalues of the Polyakov loop is a nice method of making yourself, convincing yourself which phase you're actually simulating of the dual gravity limit. So right here, I show some results, and the most interesting is this plot here, in which I show the perturbative result, which is given by that red. So the red triangles are the results from the numerical simulations. So at weak values of the coupling, we hit the perturbative prediction, which is 0.076. And as we go to strong couplings, we see this functional form of the dependence of the critical temperature on this coupling. So as we increase the value of G, T by mu, the critical temperature, in units of mu, moves up. And that is the gravity prediction which you have right there. So we still are working on this, and we want to reproduce the form of this. So we want to actually write down how T by mu can be fitted to a G by some function. And the way we find out that critical temperature is by looking at the Polyakov loop, as I already mentioned. So we plot this Polyakov loop, and then you find out where the transition is happening. In this plot, what you can see is the quantity trace of x squared. So you see a clear breaking between the SO6 and the SO3 R symmetry group in this BMN. So for example, at finite value of mu, there's this SO3 lying down, and the SO6 is clearly over it with a finite gap between them. As you decrease mu, this gap closes down, and at mu equal to 0, it has to vanish because you restore the SO9 symmetry group. I should also mention here that the SO9 symmetry in the BFSS corresponds to a horizon topology of S8 in the dual gravity theory. And when we add these mass terms, the S8 topology of the horizon in the BFSS model is deformed, and you can have it can break up into S2 cross S5 or something like that, but it no longer remains exactly S8. It becomes deformed S8. There have been a lot of work on understanding the topology in this BMN model. So now I go to the 1 plus 1 dimension. The story remains the same. I'll just skip this slide. There's nothing which I have not already mentioned. We again look at this Polyakov line. Another thing which I should say is that this Euclidean time cycle is contractible in the sense that we look at the static black holes. So they always correspond to the Polyakov line not equal to 0. So they're always deconfined along the time direction. And as I mentioned, the homogeneity of the horizon is taken to indicate the eigenvalues of the Wilson line, whether they are uniformly distributed or localized and so on. So in 1 plus 1, we can introduce this dimensionless coupling in terms of, since lambda is dimensionful, I use appropriate powers of beta and length scale to make it dimensionless. And the main motivation of studying this 1 plus 1 dimensional theory is that there is a well-known result, which is known as the Gregory-Laflamme instability, that when we consider the black hole in higher dimensional space-time, it can have topology changing. The horizon can have topologically changing situation in the sense that it can be going from a localized black hole to a uniform black string. And for this model, there is the exact prediction that there should be a transition at around alpha square RT of 2.45, where alpha is the aspect ratio of the side. It's just the spatial length by the temporal length. And R tau is defined as square root lambda times beta. This is like a topological transition on the gravity side because the topology of the black hole solution is changing, and this is dual to the deconfinement transition on the gravity side. In fact, in this model, when we are working at the large n and weak coupling limit, there's also conjectured to be this Gauss-Witten-Wadia transition at weak coupling and large n limit in two-dimensional lattice theory. And we study this on the A2 star lattice. So this is the basic phase space which we are aiming at, which we know from gravity results and the perturbative calculation, that there is a deconfinement transition, and this is like a Gauss-Witten-Wadia. And then as you increase the coupling, you enter this gravity limit, and in this there is a gravity D0 phase, which is the localized black hole phase, and there's a gravity D1 phase, and there's a transition between them. And the transition line passes through this curve, which is given by RL square is equal to some constant times R beta. So this is the expectation which we know. And this on the right, what you see is the exact numerical simulations of the same thing. So this curve is that curve shown in blue there. This thing is the red curve there. And as we go to bigger values of the coupling, we see that we reproduce the weak coupling Gauss-Witten-Wadia. But as we go to strong couplings, because we have n equal to only 16 right now, we're not strictly in the large n limit, and we are also in a finite volume. So identification of this phase transition is a little tricky, and there's a lot of, the error bars are growing on the topmost point. So ideally, if one could simulate at a larger value of n, one could probably be much closer to this red curve, and we are working on that. And for example, in this plot, you see the thermodynamics of the different phases. So for example, the D1 phase and the D0 phase have their own thermodynamic predictions and the coefficients and the power law. In this case, you see the dashed line is the supergravity prediction in this theory, and the triangle circles and the hollow circles are the lattice results. So as we go to sufficiently small values of t, we seem to hit the supergravity prediction. But we cannot do such a nice job as in 0 plus 1 dimension because we still have not have much large values of n. So if one could do larger n, one could try to study the theory at lower temperatures and do a better job. So these are again the way we identify the transition is by looking at the susceptibility of the Polyakov line, and this is peaking around that region, so that is the critical temperature. I again show you the localized and the uniform black hole solution. So this is that one there is uniform, this one is localized, and this is in the process of getting localized because as I increase the value of n, it is going from a uniform phase, green, red, black, to a localized phase. So these are a nice way to identify which phase of exactly are we simulating in the super Yang-Mills theory. So after 2 dimension, I'll just mention that we are also trying to understand this 3-dimensional super Yang-Mills, which is dual to uniform D2 branes, because P is 2, so DP branes, uniform D2 branes. And we are also trying to understand this, calculate this static quark potential by calculating what is known as Marlesina-Wilson loop, which was predicted in this paper. And it has a well-known dependence in 4 dimensions where the potential is assumed to go as the square root of lambda. So this is a calculation which was done entirely on the gravity side, but we want to do this numerically and check whether this is entirely correct. In fact, this potential can be derived in lower dimensions as well. For a p+1 generic super-Yang-Mills theory, the potential goes as lambda to the power 1 by 5 minus p. Some speculative work is that can we calculate or understand this entanglement entropy on the lattice, which seems like a far-fetched work, but we are thinking about that. And can we calculate this for the supersymmetric theories in lower dimension? For example, calculate this quantity in 1+1 dimension and see whether there is some signal for the phase transition between the black holes. Okay, so that was my first part of my talk. Okay, fine. I should be hurrying. Yeah, okay. So, in the second part, this has been work I've been involved in the last 1 year or so. And the motivation to study tensor networks is manifold, in my opinion. The first is to formulate gauge theory in terms of tensor, enables us to study theories where maybe conventional Monte Carlo methods are failing. For example, if there is a sign problem, we cannot understand the numerical aspects of a gauge theory, then why don't we understand it using tensor networks? The second is, this tensor networks provides an arena for studying lower dimensional critical systems and gap systems much more efficiently than any other numerical method. And there's a lot of physics to be understood just by using tensor networks in those lower dimensions. And thirdly, most importantly for me, is that these tensor networks are thought to play some role in putting ADS-CFT on a firm footing by understanding the properties, geometry in some sense, of the bulk from the quantum state at the boundary. So since I have some experience in holography, I thought that I should start working on tensor networks so that I can form some connection, understand the connection between the tensor networks and holography, and maybe do these supersymmetric theories and understand them better. So this is some of the motivations. So we start with a very simple theory because we want to get used to this idea of tensor network, how this works for some very simple gauge theory. So we just consider this 2D non-abelian gauge theory where you have an action which has a standard Wilson term, and then you have an action which depends on the trace of U, which is like the matter coupling, and we work in a unitary gauge, so we make all the transformation and we write down the action in the unitary gauge. The first is this the standard Wilson action which features a plaquette, and the second depends on the link. What we do then is that we expand these in terms of Boltzmann weights, which is also known as character expansion, known from strong coupling studies of lattice gauge theories. And we write down this weights as a sum over representation, where representation is given by small r, and characters, which is written as chi. And then we take the product over all the lattice sides. And similarly for the matter action, we do something like this. It is important to note that this function f depends on this described in terms of modified Bessel function of first kind. So this is what we have for this. So the next step is to write down the link and the plaquette tensors for this action, because we had a Wilson action. So Wilson action will be written in terms of plaquette tensor, which is called B in this case, and we have another tensor which is called A in this case. And we see that the B tensor is 0 if the incoming representations from left, right, above, and below are not all equal. So you have there are 4 links, and we denote this by left, right, above, and below. And if they are not the same, it's 0. If they are the same, then we have this functional form on the Bessel function. And similarly for the A tensor, we have something like this. So this tau just represents that this is the link along the time direction. You can have the corresponding link along the space direction. With the knowledge of these two tensors, one can build up a fundamental tensor. So just by using this A and B tensor, we can write down the fundamental tensor, which I'll just show in the next part of my talk, in the next slide. So let me just show the diagrammatic representation of this A and B tensor. So for example, this is the A tensor along, for example, say along a given time slice, and this is the A along perpendicular direction. They have magnetic quantum numbers and representations. They have 3 indices. They are combined into one. So this is a 2-index object. This is again a 2-index object. And my plaquette tensor is a 4-index object where I combine these 3 into 1 index and so on. So I have 2 different tensors represented like this. And this is repeated over the lattice to construct. So this is used to construct the fundamental tensor, which is then repeated over the lattice. So how do we construct the fundamental tensor from this A and B tensor? What we do is we do a Cholesky decomposition of this tensor A, and then which is roughly equal to so the L is roughly equal to the square root of the A tensor in the previous slide. And then we put a square root of A to all the 4 sides of that plaquette tensor. So for example, the A tensor is decomposed like this in 2 semicircles, and then I take a semicircle and attach it to all the 4 sides. So that means there's a B tensor sitting in the center, and then you contract the indices such that you have 4 L's hanging neighboring that B tensor, and then you sum over internal indices so that you're just left with 4 indices, which is I, J, K, L. So you have the fundamental tensor I, J, K, L 4-index object in terms of beta, which is the gauge coupling, and kappa, which is the matter coupling. And once we explore the translational invariance of the lattice, we can make several copies of this tensor, and then we get the entire lattice. So we write the partition function, and then we coarse grain this network. Yes?
Sorry, before you start coarse graining it, is this an exact representation of the partition function you are interested in?
In the sense that after, yeah, I already truncate to some value of R.
So the representations of the gauge group.
Yeah, they're already been truncated when I construct this Z. Yeah. So, I didn't mention that. I should have mentioned that. When I construct this Z by combining these T tensors, the one truncation has already been done on the representation of the gauge group.
And so you need to check that this was a
yes,
truncation?
Yes, exactly. Yes. So we have a truncation over the irreducible representation of the SUN gauge group, and we use this HOTRG method to implement the coarse graining, and we just truncate the local space to D bond of 50 right now, where D bond is sometimes also referred to as chi, and we chose R max equal to 1. So for example, R max equal to 1 means that I'm taking the trivial, fundamental, and the adjoint representation when I'm writing down the partition function. So I keep all the first 3 representation, and that corresponds to this initial tensor. Now, the choice of R max depends on what kind of gauge theory we want to study and what is the properties of that gauge theory. For example, if the gauge theory has a running coupling constant, or for example, the coupling constant is not running but slowly changing, which is sometimes called walking, then you have to use some different R max. So the choice of R max depends on what gauge theory you want to study. And the choice of R max also depends on what action you chose to represent the gauge term. For example, in this we use the standard Wilson action, where also some proposals that using a heat kernel action might be better, but I have no idea about that since I have not used it. But truncation on representation can be is a delicate choice which you can make by studying the theory with different ones and action. Yes?
So is it true that you sort of expect the truncation to be good sort of at strong coupling? Is that this is usually at weak coupling you have a very large number of representations.
Yes.
Sort of peaked in the other variable, whereas...
Yeah, so the choice of the R max you make is also depending on what whether you are weak coupling and strong coupling. So that is true. So but the way we decided what R max should be used was we did a similar calculation using the Monte Carlo simulations, and I was talking to Giffrey about this. There might be a better way of doing this, but what we did was we did the Monte Carlo simulation, and we calculated, for example, the free energy, the susceptibility, and so on. And then you started with some R max, and you saw that as you increased that R max, it started to converge to that results. So you declare that that is a good sufficient truncation in the R space.
Can I ask, you started, or you had in words in mind a continuum theory, and then you wrote down a lattice action, and now you're writing down a tensor network. Is the is the aim at this stage to see that you can reproduce sort of standard lattice results?
Yes.
Or is it to reproduce the continuum?
No, in this model, the lattice results have reproduced the continuum results. So our aim is to reproduce the lattice results. Yes, yes. Because this is just a first pass at some. Yeah. This is a very simple theory, but we want to understand this before doing other complicated gauge theories. So since most of the results are already in the literature, we thought of studying this and seeing whether the tensor is efficient or we understand it or not. Okay. The interesting thing which we have to study in this tensor formulation is the Polyakov line, because there is conjectured to be some sort of different phases in this model, and the order parameter is the Polyakov line. So how do we study Polyakov line in this tensor formulation? Is that the Polyakov line, we choose a representation, we fix a representation. For example, in this case, I fix d of half, or you can choose, since we have R max of 1, we can fix R max equal to 1. And then you write down this Polyakov line. This amounts to inserting this impure tensor or a new tensor, which is A tilde here. And that tensor can be introduced in the lattice. So once we coarse grain along a time slice, this tensor can be inserted anywhere we want because of the translational invariance of the lattice. And then we can calculate this expectation value of the Polyakov line. And this expectation value of the Polyakov line will tell us about the different phases when we'll study this. So this is one of the important observables we monitor. There are exact results known for beta equal to 0, so we just check them whether we reproduce that. In beta equal to 0, there's no gauge term, there's just the matter coupling, kappa. So the exact result is provided by this formula, and we plotted it. So here you see the dashed lines are the theoretical or the exact result known from the strong coupling expansion, and the dots are the results which we get for different system sizes, and they completely agree. So we are sure that the matter sector the tensor formulation is capturing the matter sector properly, and we are calculating the right Polyakov. We calculated other observables like the second derivative of the log z with respect to kappa to define this matter susceptibility, and we noted that there's a factor of 1,000 computation time difference between the Monte Carlo results and the TRG results. So this already tells me that in this case itself, the tensor is a much efficient method of simulating this theory. The black squares and circles you see here are the Monte Carlo results, and the colored ones are the TRG results, and they completely agree with each other. Another interesting thing is to measure this Polyakov loop correlation, because that can tell us about the confining and the Higgs phase. For example, in the limit when the temporal extent is very large, equivalent to a 0 temperature condition, the correlator is supposed to go as exponential of minus beta times V. Now, if V depends on R, then we have an area law where the slope of V versus R gives you the string tension. On the other hand, in a conformal theory, for example, the potential is Coulombic. So, for example, V goes as 1 by R. And in a Higgs-like region, V is independent of R. So V can depend on R in 3 different ways, corresponding to the confining, conformal, or a Higgs-like region. There are 2 distinct phases in this theory, confining and Higgs phase, and we'll see the results related to that. In this case, you see that the potential is proportional to, this is a proxy for R, so V is proportional to R, and we are in the confining phase. But as we go to larger values of kappa, we see that the confining phase starts to become constant, and that is an indication in some sense that it is going from the confining phase to the Higgs phase when we increase the value of kappa from 0.5 on the left to R equal to 2 on the right. So we think that there is a crossover around 1.5, but it's still not clear whether we see a real phase transition. Now, another thing which we measured was the mass gap. So we looked at different lattice sizes, NS, and then we diagonalized the transfer matrix, and we calculated the eigenvalues of the Hamiltonian, and then we have a proxy for this correlation length, that A by zeta, where zeta is the correlation length, goes as the log of lambda 1 by lambda naught. So when lambda 1 is going close to lambda 0 and this gap is closing down, the correlation length is diverging. as we can see that on bigger lattices and when you go to strong values of kappa, it seems that the correlation length is increasing. And in all this, you take the beta to be the beta equal to infinity is the continuum limit in all these cases. So you take the number of sites to be as big as possible, and that corresponds to the continuum limit. So though we saw a lot of agreement between the hot TRG and the Monte Carlo result, we saw that there is some discrepancy, and this is denoted by this vertical plot here. These are the differences between the Monte Carlo and the TRG results. And we checked this versus D bond, and it seems like when we go to strong values of kappa, we need to have a bigger D bond to get to the Monte Carlo result. So this is a hint that there might be something at play at strong values of kappa, which we still don't understand, or maybe we have to use other alternatives. So we are exploring that possibility. Okay, so I'll just end with the prospect for future work. For future work, it is important that we parallelize our code over the number of colors. So right now we have a parallel code over the number of lattice sites, but we are thinking of parallelizing the code over the number of colors, and that will help us to get to larger values of n. Another possibility is to look at the static potential in three-dimensional super Yang mills, and also if we can measure sometime in the near future the entanglement entropy, because for example, in three-dimensional n equal to 8 super Yang mills, it is known as the behavior of the entanglement entropy is known as a function of n in this paper by Rui and Takanagi. So it changes. So free field result is obviously n square, and then the IR fixed point result is n3 by 2, and they mentioned that this n to the power 5 by 3 is between this IR result and the free field theory result. So it might be nice to check the n dependence by doing some numerical calculations of the lattice supersymmetric theory. There are other possibilities to measure the Renyi entropy and the Neumann entropy in this non-abelian model, and we also plan to revisit some BKT-like phase transition in classical XY model with this more efficient tensor algorithms. Okay, thank you.
Any questions for Ralph?
So you're trying 1 plus 1 with tensor networks? 1 plus 1 dimension?
Like supersymmetric or?
Yes.
No.
No. The results you just described were for experiencing 1 plus 1?
Yeah. 1 plus 1 non-abelian gauge Higgs. Nothing to do with supersymmetry. There's no supersymmetry. Yeah.
I wouldn't know.
Yeah. Sorry. Yeah.
So
the second part of the talk was completely non-supersymmetric.
Non-supersymmetric. Sounds good. So this is just you're testing.
Yes.
These techniques to see if they work.
Yeah, exactly. Yeah.
And what do you expect to do with them if they work?
No, so the idea is that first we want to see that we can do at least any non-abelian gauge theory. That was the first kind of thing that you can do it. And then you move to some complicated, for example, you can do this theory, for example, with SU3 and so on. You can start moving to large values of n, for example. You can do SU3.
Large values like.
Yeah, large values like.
I'm with you.
Yeah, large values like anything greater than 2. You can do a general, for example, you can do SU3, SU4 and see how the behavior depends on n. Because eventually you want to at least understand how you can study non-abelian gauge theories with SU and gauge groups, at least even when n is small, using this.
But is there hope that you will connect to holography at some point?
No, the connection to holography is not very clear. So this is like a route which will take you to some point, and then you have to make that leap of going to discretizing supersymmetric theory, which is very complicated. But yeah, this will at least give us a handle of how to tackle a non-abelian SUN gauge theory, and then you bring in supersymmetry and talk about those theories, which is more complicated at some time later, maybe. Yeah. But this is also non-super, and this has no, to my knowledge, there's nothing to do with holography, at least in the models which we are looking at, non-abelian models. This is for better understanding of what people have already studied with lattice gauge theory. You find some better way of understanding it and faster way of reproducing those results. Yeah.
Can I ask, on one of these slides around there, you said I got a factor of 1,000 saving.
Yeah.
Is that something though that it must be scaling with the size or with n or
No,
okay. Just 1,000 for your example.
So for example, if I run the Tensor algorithm on my laptop and I run the same Monte Carlo results on the laptop, and I want to say, for example, do at any value of lattice and fixed value of kappa, the time it takes is a factor of 1,000.
But what's the system size?
System size, we can do 32 square.
Oh, that's the system.
Yeah, 32 square is the system size. As you,
it's 1,000 for all of those.
Yeah, mostly it's a factor of 1,000 for whenever. So for example, as you can see, there's no black corresponding to this violet because we couldn't do Monte Carlo for that big system. It was too long. So given that you can do both of them on your laptop, it's a factor of 1,000. That is what I meant by this slide. Yes.
You mentioned parallel parts of your code. So Monte Carlo, you can parallelize easily, right? But you said you can parallelize in the number of sites in your TRG?
No. I parallelize over the number of sites in the in the supersymmetric code.
Oh, okay.
Not the.
Oh, that referred to the first part of the.
Yes.
Okay, sure.
So the basic. So there's two parallelization when we talk about supersymmetric theory. There's a parallelization over the number of sites, system size, and there's also a parallelization which people have done over the number of colors. For example, you can, if you start with the SU32 gauge theory, supersymmetric gauge theory, you can put them on different cores and you can just be simulating SU4 8 times or something like that. There's some very, I don't understand it yet, but there's also a way of parallelizing over n, which is more non-trivial than the volume parallelizing.
But I mean, in this comparison.
Yeah, in the TRG thing, there's nothing is parallel.
Right. So presumably, in terms of the number of processors, the Monte Carlo would still scale better in the end. You know, if you add enough processors, it'll make the Monte Carlo faster.
Yeah, exactly. This is just on a given, for example, given laptop. With, exactly.
It's nice that you can do it on a laptop.
Yeah, yeah.
Okay. Let's take one.
Yeah, thanks.